I wanted to start off by talking about organic chemistry, and let me be a little bit more specific about that. Because I was pondering, why is it that organic chemistry is so hard? You know, and let's talk about that before we start off in this class. You know, when you learn to spell, it seems hard, but it's way more manageable than organic chemistry. If I had to teach you the word cat, you know, I might show some letters, C, A, T, and you learn the meaning of each of those letters. But what would happen if when we were teaching you how to spell, the letters could change their shape? They could fold over, maybe. They're only two-dimensional, but what if they could fold over? How much more difficult would that be if I told you, oh yeah, that's still cat, do you see that? And what would happen if they could rotate around in different orientations, C-A-T? And what would happen if you could have different populations, lots of A's and lots of C's and maybe catalytic amount of T's? You know, look, it's cat, C-A-T, cat. Everybody can see cat. It's hard. Organic chemistry is hard for these kinds of reasons. And so I just want us to all accept the fact that organic chemistry is hard, and you're really doing something that's incredible here. First of all, we don't deal with 2 dimensions. That's lame. Everything we're showing you in this class is a 3-dimensional molecule. In addition to that, molecules can move around in space. There's 3 degrees of translational freedom on top of that. So it's not just to the 3rd power, it's to the 6th power of difficulty. There's also 3 degrees of rotational freedom. Molecules can tumble around and rotate in space in 3 different axial dimensions. In addition to that, and I feel like this makes it extremely hard, as molecules can have different conformations. If I draw a hexane molecule with 6 carbons, one person will draw it with all the bonds zigzag, the other person will draw them kind of curved around like a 6-membered ring. And so the fact that every time I show you a molecule, I might be showing it to you in a different conformation makes it extremely difficult to grasp. Now, you have to think about molecules being catalytic, being present stoichiometric. Sometimes we tell you about using them in excess. And so populations of molecules we cannot represent accurately. We draw one molecule, and it is up to you to recognize that they are present in different amounts. And those concentrations can span 1 molecule in a liter or 1 molar, 10 to the 24th molecules in a liter. And we expect you have to grasp across all 24 orders of magnitude of concentration. Wow. Now, in addition to that, when I draw a molecule out, it is fully assumed that you can appreciate which of these atoms in that molecule are reactive and which ones are not. And that chemical reactivity, whether it's nucleophilicity or electrophilicity, span a massive range. Nucleophilicity of atoms like this nitrogen versus the CC bond here, those span a massive range, 60 orders of magnitude in nucleophilicity. And if you're talking about electrophilicity, like the ability to, how come you don't ever deprotonate that HC bond? You know, electrophilicity spans 170 orders of magnitude. That is way more than the number of atoms in the universe. So, if you feel like organic chemistry is hard and it's not quite obvious to you why it is so hard, you're thinking in this class across way more than 12 dimensions. Vastly more than 12 dimensions because of this conformational issue. Depends on the number of bonds. And you're thinking across hundreds of orders of magnitude. Nothing in your life that you deal with in the everyday world prepares you to think across more than a few orders of magnitude. And so this is why organic chemistry is challenging. I want to honor you for being in this class, for making it through Chem 51A and Chem 51B and the G-Chem series in order to make it here. I'm not going to pretend that this is a difficult class, but I know that all of you can do it. You know, prior sections of organic chemistry have made it through all of this. You've made it through 51A and 51B, and that's why I'm absolutely positive that you can make it through this class. And we're not going to pretend that it's easy, it's hard, but I know you can all do it. Okay, so great job making it here. Now, I always start off by talking about why is it worth, if it's so hard, why is it worth investing your time in organic chemistry? And I believe it's worthwhile for everybody, whether they've gone to college or not, to understand something about organic chemistry. So I'll try to give you my perspective on why I think organic chemistry is worth investing in. And the number one, I think, thing that I think about when I talk about organic chemistry. When people ask me, what do you do? I'm an organic chemist. They have no idea what that means. Well, we design and build drugs, atom by atom and bond by bond. Every single pill you have ever taken in your life that is a prescription pharmaceutical, and many of the ones that you buy at the grocery store over the counter, are made by synthetic organic chemists, atom by atom and bond by bond, using reactions that they learned in a class like this. They sat in a class like this, learned how to construct molecules, and then went and designed new medicines for cancer, for Alzheimer's disease, for diabetes. That's pretty cool. And if you go off into some profession where you're prescribing drugs, it's expected that you know that, oh yeah, this beta-lactam with a 4-membered ring is probably going to be similar to this other beta-lactam with a 4-membered ring, and could cause some sort of an allergic reaction that kills people. So every single drug that you've ever taken in a pill, and again, many of those some of the injectable drugs that we have nowadays are also designed and synthesized by synthetic organic chemists. Computer chips. You're all holding some sort of a phone or a device probably, or you have a computer at home, and they all use computer chips. All of those computer chips were made using a process called photolithography. They take this organic chemistry goop and they smear it on the silicon wafer, and then they shine light, and wherever the light shines, it etches a pattern. And that goop is based on organic photochemistry. Without the organic photochemistry, you could not make any computer chips anywhere on the planet Earth. The chemical engineers that are going into that field understand these organic reactions because they sat in a class like this. These flexible displays that you see nowadays, the bendable phones or the curved TV screens, they're all OLED screens, organic light emitting diodes. Right? You know that the organic chemistry piece tells you that they're based on, you pass some electricity through molecules and then they emit light. And those are all organic chemistry molecules made by people who sat in a class like this and learned some organic chemistry. And if you want to understand how they work, how to make them better, how to make the next generation, how to make them more efficient, then this is the place to start with that. Or just to understand how your phone works, right? How do you get blue light by passing electricity through a molecule? Plastics, materials really is the broader term. Pretty much everything except this metal railing over here is organic. The seats that you are sitting on, the fabric that you are sitting on is some sort of a synthetic polymer that was made by an industrial polymer chemist who's an organic chemist. The backing of the seats is plastic. This material that this countertop is made out of is plastic. Everything is plastic unless it's metal or ceramic, right? If you look around, it's like how many things in here are made out of metal or else they're ceramic? That's a very small fraction of what's in this classroom. And the world, the future, is not just simple dumb plastics. I don't want to say that they're dumb because the dynamic range of materials properties for plastics is amazing. But synthetic chemists who sat, or organic chemists and polymer chemists who sat in a class like this are developing smart materials, materials that will glow whenever there's a fracture that's about to occur, materials that can heal themselves whenever you break them to the point of making a crack. You just let them relax and then suddenly they re-heal to be as strong as they were before. All of these are based on organic chemistry reactions. The future of technology, the technology you hold in your hand, on your phone, on your device, in your seat, it's organic chemistry. It is so central. Now, I don't expect many of you to go into chemical engineering or to go into the drug industry and design medicines to cure cancer or Alzheimer's disease. Many of you are probably in this class because you are interested in going to some sort of a professional school, to medical school, to dental school, optometry school, pharmacy school. Every single one of those schools expects you to know organic chemistry. When you prescribe a drug or you study biochemistry, it is all based on organic molecules. And there's the expectation, or if you go to graduate school in chemistry to go become a medicinal chemist, you need to know organic chemistry. And you'll have to take some sort of an exam where they're going to test you on the stuff that you learned in this class to see, did you really get the tools from that class and can you remember how to use those tools? Now, when you go take these examinations, the MCAT, the PCAT, the OAT, the DAT, right? most people spend their time practicing before they take those exams, and there are preparatory classes to help you prepare for organic chemistry. So you might be thinking, I just want to get through this class, and then I'll learn the material when I take the Kaplan prep course or something. Those courses are not going to teach you from the ground up. They are review courses. They are courses that assume that you learn the material first, and they're just helping you to review. You cannot pack all the learning of a year of organic chemistry into 1 week. That's not going to happen in a useful way. So you need to invest, even if you're thinking, God, I just want to make it through this class because my future goal, it's required for my degree. I'm not quite clear how I understand it. I promise you, if you invest in this class now, all of that hard work will pay off when it's time for you to take one of these exams. These are expensive. You have already paid me, and you have already paid our instructional team to help you. So take advantage of that. Okay, let's talk about who's running this course. This course is run by the University of California at Irvine. They run the course. Now, they have hired me to assess you and give some grade to the registrar at the end of the quarter. They could care less about who I am or what I do. So you may think that I'm some evil operator here trying to destroy your life or raise your life through some grade. It's like, I'm just like you. I just, they told me I need to teach this course, which I love teaching organic chemistry. That's great, but I hate assigning grades. So really, this course is run by the University of California, and I want to tell you about the people who are on your team to help you master the material and make the best grade possible. So first of all, this is me, Dave Van Vranken, Dave, whatever you call me, whatever you want. I'll call you whatever you want me to call you to just be respectful. Jason, we've got 2 TAs here in the class, Jason Combs and Daniel Sion. They're graduate students. They are amazing. They know a ton of organic chemistry. They have invested their lives in organic chemistry just like me. And I promise you, they want everyone in this class to understand organic chemistry. I would love it if everyone in here fell in love with organic chemistry. And maybe if we had organic chemistry class and no exams and no grades, it would be awesome. We have to deal with that, unfortunately. That's kind of like my ideal teaching situation. Now, your goal in this class is to understand organic chemistry. It's kind of like making an ascent on Everest. And not many people have done that. It really distinguishes people who are pathologically motivated in some way. But nobody just says, you know what, I'm going to go climb Everest today. That doesn't happen. You have to organize an entire team to make an ascent of Everest, to make an assault on the top of Everest. And you don't just hire random people that you find here in Irvine or in local city. What you do is you hire Sherpas, right? These are an ethnic minority, like Tibet or Nepal or somewhere around there. People are used to living at high altitudes and can carry heavy weights, who know the terrain. They are experts at navigating the terrain. And you are not going to make it to the top of Everest without a powerful team of Sherpas to help you load your equipment up to the base camp so that you can make it to the top. Notice the Sherpas do not pick people up on their shoulders and carry them to the top of Everest. No matter how much you pay them, they don't do that. They are there. They're the team that helps people make that ascent. And we are your team. We are your Sherpas. You have paid us to help you make that ascent, right? You've paid us money. When you sign those checks over or whip out your credit card to pay tuition, you've paid us money. And so my best advice to you is to use the hell out of us, right? Not in a disrespectful way, but don't waste your money. You've already spent the money. All right, here we are. We've reached the 3rd quarter of organic chemistry here at UC Irvine. I'm doing everything out of the 6th edition of the textbook. It's a little bit different from the 5th edition that hopefully nobody's still using that. There are some tools to translate the different versions on my website from fall of last year. And this is going to be incredibly challenging because there are lots of reactions in Chemistry 51C. Like, how many different reactions did you learn in Chemistry 51A? Like SN1 and SN2 and E1 and E2, which is not really useful to anybody. And then suddenly you get to Chem 51B and they start loading you up with reactions, hydroboration, oxidation, pyridinium chlorochromate, And it might have felt like, gee, that's a lot of tools to learn. That's nothing, right? In Chemistry 51C, from the first day of this class, later we're going to get to this, I'm going to start loading you up with reactions because that's the way the book is structured, that's the way the subject is structured, and I expect you to master those chemical reactions as tools so that you can predict any product that reaction is applied to. So we're covering in this course chapter 16 through chapter 23. It's just like all the sections of Chemistry 51C in the spring. That's what we're covering. And there's a lot of material in there, and we can do it. So here's a roadmap for what we're going to be doing. You know, chapter 16 is a massive chapter, and it is a departure from the types of chemistry that you've had in the previous 15 chapters of our book. And so I'm going to have one exam just on chapter 16. So we're going to cover chapter 16. It's our chance to get really back into the swing of things with organic chemistry. You know, for those of you who might have finished the prerequisite class during the summer, might be fresh in your mind, but some of you, it may have been months since you've taken organic chemistry, year or years if you've taken organic chemistry, and that's hard. So our first exam will be just on one chapter. And you may think, oh, that's easy. I don't need to step. It won't be easy. It won't be easy. Look at all this in our next exam. Our next midterm exam is 4 chapters, all centered around adding nucleophiles to C double bond O, right? And you really need where it's just going to be a lot of work. And then we have one more midterm after that is covering a class of nucleophiles called enolates, making carbanions in a way that you've never seen before. And then the last chapter on amines. That's kind of like drugs. Every kind of illegal drug or legal drug is probably an amine of some kind. And then we're going to, during finals week, the first day, on Monday morning, we'll be here taking a final exam where we're going to test, you know, in a cumulative way, do you remember those tools? Okay, that's our quarter here. So our first exam is in a couple of weeks on chapter 16. So you need to start getting ready for that. So here's the way I determine the grade in the class. There's 3 midterms in this class, and each one of those midterms counts for 20%. I don't drop the lowest exam score in this class. We did that in many of the classes at UCI during the height of the pandemic, and like many other courses, that's not part of the course anymore. You know, if you do horrible in these exams, you know, I tell you, and here's roughly the grade breakdown. I got this from some biosci website years ago, so I'm trying to follow the same type of grade distribution they have in biological sciences. And so I'm just going to take the class and cut it according to these percentiles and then assign the grades in that way. If you make over 90% of the points, like if it's a 200-point exam and you make 180 points, I'm going to give you an A. I don't care if you failed every single exam up to that point. If you can get over 90% of the points, I am absolutely positive that you know the material. There's just no way to make over 90% of the points on a cumulative exam. Stay on the material. Even if you don't do well in the first exam, just stay on it for the next exam. You might think, well, I wanted to get an A+, and now my dream is over, so I'm going to give up. Don't. You'll be using that material later, whether you retake the class, whether you take the Kaplan review prep course, or you're taking some tests to get entrance into optometry school. You'll use that information. Stay on the material. It's worth it. I couldn't fit this on my horizontal slide. This is our course calendar. It's not published anywhere. I just use this with my instructional team to help organize our time. But you can see we have 2 weeks, and then that following Monday we have our first midterm exam. And then we cover more material in lecture. We finish covering that in discussion section, and unfortunately there's Veterans Day, and then the following week we have an exam. So similarly, we cover the final material in lecture, we finish covering it in discussion section, and then I give you an exam on that. And that's the general flow of the class. Cover it in lecture, and usually the next week we're having you review that material and practice those tools in discussion section, and then we have an exam when we're done doing that. Now it is up to you to work additional problems. There will not be enough problems in discussion section, And there will not be enough problems on these quizzes that I'll talk about shortly on Canvas to prepare you for my exams or for the types of exams that any instructor at UC Irvine asks in 51C. You need to work problems in the book. But let me go back and talk about discussion section. Here we are in our weekly calendar here. So this is our days of the week here, Monday, Tuesday, Wednesday, Thursday, Friday. And here you are. Thank you for coming, or I guess it's a Friday. Thank you for coming at 8 a.m. I honor you for being here so early in the morning. We have discussion sections on Monday, Wednesday, and Friday. The discussion sections are not required, but I expect you to be there. There is no better place for you to be talking with other peers about organic chemistry, trying to solve problems together as a team, developing relationships that will last far beyond UCI. By the time you get from UCI, you're not going to remember the Diels-Alder reaction or whether to use chromic acid or potassium dichromate. Nobody cares about that. But the relationships that you build and the network that you build in your classes at UCI are the real value of your degree and why it's worth paying money to come here to UCI. Go to discussion section, hang out with other students, decide to study together or not, find people that you can communicate with. Hey, I missed the last discussion section. Do you have that worksheet? Build a network. Right? This is what makes it valuable to come to a top-ranked university like UCI. So we don't take roll in discussion section or attendance, but we expect you to be there. If you miss your discussion section, go to a different one. Right? As long as there's seats, don't take a seat away from somebody who actually registered to be in that discussion section, but we don't take roll in there. And we have amazing learning assistants who are there to help you break up into teams and then work on problems together with your team of students. We'll break a discussion section up into teams of 2 to 5 people. Each of the groups will be assigned a problem. And then whoever is picked at random will go to the board and show the rest of the class, here's how our group thought about this problem, right? And you may be thinking, no freaking way am I getting up to a board and talking about chemistry in front of other students. Like, what if I'm wrong? Okay, you're wrong. I say stupid stuff all the time when I'm up in front of you, and it doesn't kill me. One of the most important skills in addition to your network is just being able to communicate about science. It may seem scary to you, and you may think, why is he making us talk about science? If you have a skill of getting up in front of other people and talking about stuff, I promise you that will be valuable across the rest of your life, in your career, in your education. That's essential, is to be able to talk to other people. So discussion section, I expect you to go. We don't grade it, right? There's no grade in there. I can't imagine a more supportive environment for you to talk about organic chemistry and invest in that. The Department of Chemistry runs something called an organic chemistry peer tutoring program. Are my peer tutors for this section here this morning? So I see one person in the class. Is there another peer tutor? Okay, maybe you can send me an email and introduce yourself. I've been watching the website to see with excitement. Sorry, what's your name again? Shout it out. Regil, welcome to our team, Regil. Right, and I'll invite you to our instructional team meetings on Thursday. We'd love to have you. Regil is part of our team, right? If you don't trust me because I'm a professor and I assign your grade, go talk to Regil. He's another undergraduate like you who's taking classes like you, and all he wants is for you to make it the best grade you can make in the class, right? You have an amazing team here and the peer tutors, and I promise you that the TAs or the peer tutors that are assigned to sections of Chem 51A, you could also go to them with questions about 51C. They all took 51C, the whole entire organic chemistry series. But Regil has been assigned specifically to our section. So he knows what we've covered in the class and the order in which we've covered it, and what a great resource. Alexis Tan is teaching LARC tutorials, right? You know, it is great to get as much experience as you can solving problems in organic chemistry. And so the LARC tutorials, twice a week, will give you structured sort of problem-solving practice and problem-solving skills, right? Isn't that what you want? Because guess what my tests are? Problem-solving. So if you sign up for these LARC tutorials, you can work with other people and think more deeply about organic chemistry than you can in a discussion section. And I love the fact that it's design like a class with specific meeting times, because I don't know about you, but I need self-discipline in my life. If something is not assigned and it's like soft on my calendar, I didn't write it down, I'll blow it off. Because I got a lot of other things going on in my life, and I know you do too. You got other classes other than Chemistry 51C. So take advantage of those LARC tutorials. And I just realized that there's this LARC after dark thing that you can go from 5 to 7. Is that new? Or maybe they've had that every year. You just show up and you study organic chemistry with other people who are studying organic chemistry math. And I assume there's a tutorial. Is there a tutorial leader assigned each one of those that can help you answer questions? One-on-one? Holy cow. Wow. That's, what a good deal. Okay, I mentioned before that I get the fact that this is an off-sequence class. That means for many of you, maybe you didn't do that well in Chemistry 51C, or things are weird and it's like you've had a whole summer since you've had Chem 51B. If I walk away from a subject for 2 weeks, like on Christmas break, I can't remember anything when I come back. I can't imagine how difficult it is if it's been 3 months since you had organic chemistry, or a year. Jeez. I mean, now fortunately, the stuff from Chemistry 51A and 51B, the first 2 quarters, it's not all useful. I mean, the sad fact is, you don't need to know everything in those first 2 quarters to be up to speed here. So if you felt like you got left behind in Chemistry 51A or 51B, what should you do? Here, I'll tell you exactly what to do. You go over to our Canvas website and you click on Module 0. And there is a whole set of Canvas quizzes on there where I try to bring you up to speed on the stuff that I think is important from Chemistry 51A and 51B. And it is not the entire book, and it is not the entire first 2 quarters. There's a few skills that you needed to take out of Chemistry 51A and 51B in order to get off on the right footing here in our class. But there is no time to do this. You have to do it now, today. Get out of here, get up to speed on Chemistry 51A and 51B, because I'm already giving you new material. And so, in a way, I'm trying to level the playing field and bring everybody up to the same level with the previous 2 quarters. So there's a whole set of little mini quizzes, a few questions each on each of these little topics from the earlier chapters in our book, and those are all required. So let me come back to this previous page with these modules. There's 9 different modules. One of them is review, and each one of these modules, except for module 0, corresponds to a chapter in the book. And at the end of each one of these modules, you'll have a quiz on Canvas, maybe 15 questions or something. I can't remember how many I have in there. And you need to do that quiz. It's kind of like a homework thing. Or it's not really a homework, it's more testing. Do you get the concepts in the chapter? Now, don't stress over these quizzes. You can work the quizzes as many times as you want. If the first time you work it, you don't get the grade, just redo it. It's the same questions. Do it until you get. So if you don't get a perfect score every time, whose fault is that? Right? That's easy to just redo it over and over again. Now, unfortunately, this program does not have a graphical interface. So I've inserted this tool called it's a Java applet, JME molecular applet, or JavaScript applet, where you can draw molecules and generate text strings that represent those molecules. And unfortunately, you have to click the smiles button and paste that string in. Here's your answer. Just like you could paste the word apple and I could grade that, or you could paste the word Samantha and I could grade that. You have to paste this text string in there. It's a modern chemoinformatics tool that allows you to describe 3-dimensional organic molecules as text strings. It could be texted on your iPhone or anything else. So that's most of the questions will involve you drawing something and then pasting the smiles text string into the answer box. And there's some practice in the first quiz module to help you understand how that works. Okay, let me come back to the modules. Each one of these modules, if you click on it, I try to post my lectures. If you look back at my public Canvas websites for all my previous courses, like in the spring, like in the fall of last year, like in the spring before, you'll see I've got modules. You could tell I copied my website, and I post my lectures. I leave lecture, I go and I edit my lecture videos using iMovie, and then I repost them later. Now, I don't promise to do that every time, but I certainly try. And so many of you are thinking, damn, now I don't have to go to this 8 o'clock. I would hope you would come here just to get your day off to the right start. But I make every attempt to post my lectures online so that you can hit stop and go and rewind and review the material and as you work problems in the book. Now, watching my lectures is not a replacement for working problems in the book. Some of you may think, well, I don't want to work problems in the book. I can't afford that stupid solutions manual. It's like costs $1 billion. Okay, so I went and I created solutions for every single problem, answering them exactly the way and formatted the way I put questions on my exams. And they're posted on our website. Don't distribute them. They're for you. But I expect you to work every problem in the book. That's how you're going to practice. If you take a surfing class and you think, well, I get the concept, so I'm ready for the exam. No. If you don't get out there on the waves and try that surfboard out and be ready for every single possible wave in the universe, you are not going to do well on the surfing exam. And this class is no different. You have to work problems in the book or any place you can get your hands on problems to be ready for the problems I'm going to throw at you on the exam. I'm going to show you problems on the exam you've never seen before. If I accidentally put a problem you've seen before in there, it's not on purpose. So you have to practice working problems, as many problems as you can get your hands on in this class. Now, how do you communicate with me in this class? So if you have questions about chemistry that involve chemistry structures, organic molecules, you ask me after class or during my study halls that I host. So we all have, I don't want to call them office hours. I hate the word office hours. It implies that you're supposed to show up with some brilliant question. You're not going to show up to any office hour with a brilliant question. Nobody does that. What I want you to do is come to my study hall, my office hour, and just sit there and study. And if you come up with a question, you can ask me. And if you don't come up with a question and you're just rocking along, awesome. Right? That's what it's supposed to be for. And the worst thing in the world, I can speak on behalf of me and the TAs and the peer tutors and the LARC tutorial leaders and anybody. The worst thing in the world is to have office hours or study halls and nobody shows up. It's like, well, you've got to study sometime. Why not study while I'm there and able to answer your questions? It's so easy, right? It's like, hey, I'm just going to, you show up, you say, hey, do you mind if I work on some problems in the book while I just sit here? And guess what I'm going to say? Oh, sure. It's that easy. That's the way you're supposed to use office hours in everybody's class here at UCI or in college. I don't know, maybe you've been avoiding them because you're afraid that the teacher's going to suddenly give you some tough exam and lower you. That's not what it's for. You paid us money to be there. Use us. Do not send me email questions or emails on Canvas about chemistry. Like if you say, oh, I was having problems with this figure 12 and there's a 6-membered ring and a bond to carbon. And how am I going to type out an answer to that? I don't want to read that. I don't understand, right? I draw chemical structures. I cannot, I hate to sound stupid, but I have to draw chemical structures and see chemical structures to answer questions about chemistry. If you have questions about logistics, right? Was that exam, the answer key posted, or what's the problem with the Canvas website or something? That I can answer by email or address by email. But questions about chemistry, you have to come and go to my study hall or see me after class to ask questions about chemistry, or the teaching assistants or anyone on our instructional team. Now, the final note that I have for you is a quote from Benjamin Franklin, a noted statesman, scientist, scholar, who said, "Drive thy business." Drive thy business. I can't imagine how much you paid or your family paid to be here. Some of you are working jobs to pay for this education. And right now, your education is your business. It's like you're a corporation, a public corporation, even though nothing's public, and your investors expect a return on their money. And so you need to take advantage of that and get a return on what you've invested in this education. And so you need to drive your business. And Benjamin Franklin was very clever and a great entrepreneur, and he understood that if you fall behind, there is no catching up. Right? There is no catching up. I say there's no catching up. It's just very hard. Because if you don't drive your business, it's drive thy business or it will drive thee. And this is true. We've all fallen behind on something and just thought, God, how am I ever going to catch up? Because everything else is piling on, it doesn't stop. And that's the way this class and every class works at a university system. So get on top of the material. When you leave here, it's early in the morning, get out and start practicing problems. Start working those first modules in our class. Take advantage of that time. Stay ahead of it. Nothing will feel better than if you get out of this class and you start working those first Canvas modules and checking those off as done. Right? Think about how good you'll feel knowing that your weekend is yours and not with this looming thing ahead of you. Now, I didn't quite mention it here. Most of our Canvas quizzes are due on Sunday nights at 11:59 p.m. Not 12 midnight, but 11:59 p.m. Just because it was hard for me to type. I couldn't remember AM or PM when I was typing 12, so I just put 11:59. So I think except for the last week, because we have an exam on Friday of the last week. So the Canvas quizzes will be due on Sunday nights at 11:59. Okay, let's go ahead and start with new material here. Organic chemistry is hard, but I know you can do it. Generations of students have done this. Now, I'm lecturing off of a lecture template. I post these lecture templates on our Canvas website. So if you go into the Canvas website, there's a tab Files in our Canvas website. I don't even know, can I access this here? Let me see if I can. Yeah, so I'm over here in the Canvas website under Files. Actually, it's if you can go to Modules. So if I go to the first module, there's a number of ways you can access it. So if you go to the first module, Module 1, right here, if I just click on that 1, it'll take you, well, that didn't work well, whatever. It takes you to Module 1. And here in Module 1, unfortunately my pen, I don't know how to operate my pen. In Module 1, it says Module 1, Chapter 16, Learning Materials. And I still have my videos from last year. I will keep those videos, or from spring, I'll keep those videos up there until I replace them with videos from this spring. And you'll note very quickly, the material's not that different. It's the same slides that I'm using to teach you organic chemistry. Organic chemistry has not changed in the past few months. And there's this link on the top that says Chapter 16 Lecture Template. And if you click on that, it should open up a PDF file, if I did this correctly, to these blank notes. And you don't have to write everything down that is on this paper. You can just fill it in as I go, the way I'm filling it in. So I hope that'll allow you to spend a little more time if you go back to the module, and this Module 1, Chapter 16, a little more time processing the information and a little bit less time writing as fast as you can. And again, the lectures will be online, so you can wait and fill it in later when I post the video for this lecture. So all these lecture, unfilled lecture templates are available on our website, on the Canvas website. They're all stored in files, but they're linked. The filled-in lecture templates? No. The question is, will I post the filled-in lecture templates? Absolutely not. But the videos will be available for our lecture, where they'll be filled in during the, so I only post the blank lecture templates. Okay, Chapter 16. You've had 2 quarters learning to identify leaving groups and substitute leaving groups. SN1, SN2, and everything that you've been doing in those previous quarters, I think, has been all about identifying leaving groups. Iodide, bromide, chloride, tosylate, protonated OH, and substituting it with some sort of a nucleophile. The nucleophiles could be water, could be amines, could be other halides. And so everything so far has been about you and identifying those leaving groups so that you could do substitution reactions through various different mechanisms. And this is going to be a liability for you. If you have become an expert at this, unfortunately, this is not what Chemistry 51C is about. Now, this came with some caveats, and I just want to spell those out for you. The big caveat here is that you can't, if the leaving groups are attached to sp2 hybridized carbons, like alkenes, or if they are attached to sp2 hybridized carbons on benzene rings, those will not ever undergo SN1 or SN2 reactions. Doesn't matter how good the leaving group is, you're not going to be doing SN1 or SN2 on these types of organic compounds that have leaving groups attached. So, great job mastering this concept of you identify a leaving group and then you substitute it. And we're not doing a lot of that this quarter. That's not how organic chemistry works. That's not how biology works. That's not how biochemical systems make DNA. It's not how they make proteins. It's not how they make RNA. Why did you spend most of organic chemistry learning SN1 and SN2? I don't know. I don't know. Let me tell you what we're going to be doing this quarter. What we're going to be doing this quarter, and starting off in this chapter more specifically, what we're going to be doing is we're going to be substituting a different type of group. The first chapter is about doing chemistry on benzene rings. So we're going to be taking benzene rings like this, and we're going to be doing substitution reactions. And we're going to show you a set of species, reactive species, powerful reactive species. We're going to have to give you some secret recipes for how to make these reactive species. And we're going to do substitution reactions. And what we're going to be substituting looks nothing like what you've been substituting in the previous 2 quarters. And this is going to kill a large number of you in this class who will be like, where's my leaving group? So let's talk about what we're substituting in this class. So what we're substituting in this quarter. So we're going to be, E is kind of this symbolic, it's like NU for nucleophile. E stands for electrophile. There's no element symbol E. So we're going to be substituting on benzene rings. And what are we substituting? The thing that will kill you is we're substituting something that we usually don't draw. We're substituting H. And we're not going to draw those H's for you. It is up to you to see every single H on every single molecule that is not drawn. No matter what I draw and no matter how fast I'm going, I expect you to know how many hydrogens are attached to every single carbon atom on everything I draw. And you've had 2 quarters to get ready for this, to move away from chemical formulas where we write CH2 and we draw every bond to every H. We stopped doing that a long time ago. And if you can't see the H's that are not drawn, you're not going to make it. You won't be able to do my exams. You won't be able to do my problem sets. You couldn't take any other Chemistry 51C class and function well. I give you practice with this on our quizzes. You can't practice enough. You have to have instantaneous recognition, whether I draw the H or not, that there was an H that got replaced there. And we're going to do this in the later chapters where next to carbonyls there are H's that get substituted, and we're not going to draw those H's for you. You have to recognize that here's what, if I ask you what happened here and you say, oh, I made a bond to E, you missed half of the concept. What really happened is I replaced the H that wasn't drawn. Okay, now what is this electrophile E plus thing? So this chapter, our first exam, is going to be about this. I'm going to give you 5 recipes today, and you need to get out of here and go practice those recipes. This is most of chapter 16 right here. Okay, so I'm going to give you 5 recipes, and they allow you to do different things here. So the first recipe I'm going to give you is a recipe for how to attach halogens to benzene rings. And notice how I'm drawing the H for you. I'm generally not going to do that in the future. And our secret recipe is to take Br2. Well, Br2 doesn't add to double bonds of benzene rings. That's right. If I take benzene and add Br2, it'll just laugh. Nothing will happen. You have to add this secret catalyst. I'm going to tell you the secret catalyst right now. It's ferric bromide, FeBr3. Now, why would you want to add bromine to a benzene ring? Didn't we just say you can't do SN2 and SN1 on halogens attached to benzene rings? That's right. But later, in a couple of chapters, I'm going to show you how to change that bromine into the most powerful nucleophile that we know in organic chemistry. And wow, is that going to be useful. Now, you can do the same thing with Cl2 and FeCl3. You can add chlorine to I'm not going to draw that for you here. It's basically the same thing. It's just write Cl wherever you see Br. Okay, sometimes we like to put nitrogen atoms on benzene rings, nitrogen substituents. If you look at most of the pharmaceutical drugs that are produced around the world by synthetic organic chemists, most of them have nitrogen attached to benzene rings. And here's our number 1 way for attaching that. We use this reaction here where we add a nitro group. Nobody wants a nitro group in their benzene ring, but you can change the nitro group into something useful. We'll talk about the structure of a nitro group later. And our recipe is nitric acid. You know, nitric acid is a dangerous acid. It's an oxidizing acid, it's a strong acid, but it's not the strongest acid that we have. There is a stronger acid that we need to add as a catalyst, and that's sulfuric acid. Sulfuric acid is a crazy, concentrated, high-powered acid, and that's what we need to activate the nitric acid. Seems weird that you have to add a more powerful acid than nitric acid to activate this reaction. That's our recipe. Nitric acid, sulfuric acid. And then we're going to teach you in this chapter how to convert that nitro group, which we don't want, into something that's into an NH2 group, really. Okay, we need to make carbon-carbon bonds to benzene rings. There's a lot of indirect ways to do that. But I'm going to show you a direct way, one-step reaction. We take this species that I don't think you've seen before, that's called an acyl chloride or an acid chloride. Depends on, the old word is acid chloride. I see that used sometimes in the book. We also call this an acyl chloride. And man, this reagent is money. Total money for you this quarter. It's not just in this benzene ring chapter. It's also going to be used in other chapters, acyl chlorides. And we need to add another acid catalyst, but this one is a Lewis acid catalyst, aluminum trichloride. So you take the R group can be methyl. The R group can be another benzene ring. The R group can be a heterocycle you've never heard of called thiophene, right? Ethyl, propyl, but this is a powerful way to make carbon-carbon bonds to benzene rings. Now we have two other recipes that I expect you to know. You've got to get out of here and start practicing using this recipe. Practice as many problems as you can get your hands on to practice these recipes. And you may think, oh, it's so simple, I'll never mess. It won't be that simple. We're going to give you lots of crazy applications of this where it's not a simple benzene ring. Now, there's 5 recipes. They're not all equally useful. I just gave you the 3 that are really useful. Now I'm going to give you 2 that aren't quite as useful. And the book seems to put these in there, plenty. But so one of the others, how do you make a bond to sulfur in a benzene ring? We can change sulfonic acids to other stuff. But this other reaction that we do, we use something called sulfur trioxide, SO3. It's a gas, actually. If you burn coal, sulfur trioxide goes up into the atmosphere, and when it rains, it comes down as dilute sulfuric acid, which can damage limestone statues and buildings. Now, sulfur trioxide is not reactive enough. We have to add an acid catalyst here, and conveniently, the acid catalyst that we use is sulfuric acid. In fact, you can buy bottles of sulfuric acid where they've bubbled in sulfur trioxide in there and use that if you wanted to. But that's our recipe there, sulfur trioxide and sulfuric acid. Okay, the last reaction that I'm going to show you is another way to make carbon-carbon bonds. And it involves you taking alkyl iodides, alkyl bromides, alkyl chlorides, alkyl halides, and you use that same aluminum Lewis acid, aluminum trichloride. That is supposed to be, whoops, it's supposed to be a C. Aluminum trichloride, it's just like that acyl chloride recipe above. Unfortunately, adding alkyl groups directly has so many exceptions. You spend more time learning the exceptions to this last recipe than you spend learning the actual rule. It's just not that useful. And the question loves to try to trip you up with questions about all the exceptions, but it just feels like it's not worth all the effort because there's better ways to make carbon-carbon bonds to benzene rings. These are your 5 reactions for this chapter. Get out of here and start working problems in the back of chapter 16 to get on this, because we are just going to keep rolling along. So when we come back on Monday, I'm going to teach you how do these recipes work, how do they generate powerful electrophiles, and make bonds to benzene rings where we substitute H atoms. We substitute atoms that we don't draw. Okay, you guys can do it. Welcome to our class. We're going to rock it this quarter.